Welcome, everybody. I see that 8 of you are already there. I will wait a few more minutes. I'm just trying to figure out the field of vision for this. What can you see? Okay, everybody. I see 16 of you are here, 17 now. Okay, welcome. And today is Big Idea 3 review. And there are two distinct parts to it. One part is Unit 7 and one part is Unit 8. So in Unit 7, we studied reaction prediction, how to write reactions, how to write net ionic equations, and how to predict the products. And then we did stoichiometry. Mostly, we did limiting reactant and percent yield. Okay, so as we did reaction prediction, so in reaction prediction, first of all, you need to remember what you can dissociate and what you can't dissociate. And you also need to remember types of reactions. So the types of reaction we're going to focus here are synthesis or combination reaction, decomposition reactions, single replacement reaction, double replacement reaction, RXN for reaction, and some consider combustion to be a different reaction and some consider combustion to be part of synthesis. Let's treat it as separate. Either way, you're not wrong. And then there are redox reactions, which we'll do when we review Unit 8 in a minute. Just to remind you, and guys, I'm going with the review of the entire topic. For those 16 of you that are here, can you tell me, is that what you're looking for? Ellen says, sure. So if anybody who is not looking for this, let me know. I will move on. Iris says, good. Animesh says, that could be helpful. Yes, yep. Okay, all right. I'm going. So synthesis or combination reaction is identified when one product is formed. And what one product will be formed? Remember, there are 5 or 6 bullet points. A non-metal oxide plus water will form acid. A metal oxide plus water will form a base. A non-metal and metal oxide will form metal. You just kind of combine them both, right? It's called a salt, right? So these are the primary things. And telltale sign is one product. For example, if they say Na2O, now you know it's a metal oxide because there's sodium in it with water. And now what base can you think of? The base will be NaOH, right? And to balance it, if you put a 2 here, then that balances this equation. This is not the net ionic equation, and I'll talk about what can you break down in a minute, but let's first go over types of reactions. So you must focus on these bullet points so you know what is formed. Pretty much whatever you can balance, you can form. Decomposition reaction is where you start with one reactant and then it can form 2 or 3 or more products. And decomposition reactions, now what products to form? You got to again remember, if it is like bicarbonate, like Na8CO3, then it dissociates to form Na2CO3 plus CO2 plus H2O. And you put a 2 here and that balances it. If it is ammonium carbonate, it forms ammonia plus H2CO3. One thing to remember here, guys, is a couple of special substances like H2CO3 is an unstable substance which breaks into H2O and CO2. And NH4OH is again an unstable substance that breaks into ammonia and water. So if I were to give you also, there is potassium chlorate, right? So when chlorates are heated strongly, they break into smaller atoms, KCl plus O2. So 2 and 2. One thing that a lot of you did last time when I gave you a problem like that, I said potassium chlorate is strongly heated. Lot of you tend to dissociate it. You identify it as ionic compound and then you dissociate in K plus ClO3 minus. Well, this is true if you were dissolving this solid, ionic solid in water. That's when it will split up into its ion. When you have an ionic compound and you take it as solid without water and heat it up, still because it's a bulky compound, it breaks, but it does not dissociate into ions, but more it dissociates to make smaller gaseous molecules that can escape like O2, CO2, and H2O, and rest remains as a solid ionic compound. So remember that. This is dissociation where you have ionic compound just breaking into its ions upon addition of water. But when you are heating a solid ionic compound in absence of water, then it breaks down to give off small molecules. Single replacement reaction is when you have, it's characterized by a single either metal or non-metal plus a compound. This is the common part of it, and you always assume that reaction happens. Here, what you got to remember, guys, that zinc and zinc 2 plus are not the same species. They involve 2 electron transfers, so you cannot cancel one against other. Double replacement reaction is when you take 2 compounds, compound 1 and compound 2, and you switch partners. And in double replacement reaction, couple things to remember is you do not have the luxury to change or not change the subscripts that come from the charges. What I'm trying to say, if aluminum chloride, let's say, reacts with sodium sulfate, right? You know, when they switch partners, aluminum will go with sulfate and sodium will go with chloride. And it could be your tendency to just carry over Na2Cl3. No, you can't do that because the subscripts are determined by charges. You got to remember crisscrossing them. So sodium forms +1, you know, from the periodic table. Chloride forms -1, so its formula would be NaCl and not Na2Cl3. And then you will form aluminum sulfate, so Al2SO4 thrice, because you would have memorized that sulfate's charge is -2 and aluminum is +3. And then you put coefficients to balance. Generally, when there is a 3, guys, you put a 2 in the front. It's hard to balance with a 3, even though there are occasions when you can, but sometimes it doesn't work that way. So if I put that, there is 6 and 3. And I think that balances the equation. And combustion is when one reactant is oxygen. And when you combust something, then you make oxide of that if it is an atom, right? So it could be metal or non-metal. Like if you burn nitrogen in oxygen, you'll make an oxide of nitrogen. If you burn aluminum in oxygen, you make an oxide of aluminum. If it is a hydrocarbon, like it has carbon and hydrogen in it, and you burn it in oxygen, then it forms carbon dioxide and water. It doesn't matter what hydrocarbon it is, it will always form that. And if it is organic compound containing CHNO, if you burn it in oxygen, it will still form carbon dioxide and water. Okay. Natasha, yes, we will get to go over the practice problems in the end. So I am still doing Unit 7's part. Now, second part of Unit 7 is drawing particulate level drawings. And as you draw particulate level drawings, guys, I want to remind you to use circles and write atoms or ions inside there. Please do not use the other legends. It gets very confusing. Also, remember what is dissociated, you keep them separate. What is not dissociated, you keep them together. Precipitate generally settles at the bottom of a beaker. If it is an ionic compound, you must draw charges. For sodium chloride, if it is not dissolved in solid, you have to write Na plus Cl minus. If you just draw it at the bottom as NaCl, you will lose point because what it tells you is it's a molecular compound when it is not. Okay, from there, I'm going to briefly remind you about types of compounds, and I'm going to remind you how to dissociate things or not dissociate them. So remember, for naming purposes, we classified compounds as ionic, molecular, acids, and bases. Ionic compounds have a metal cation plus an anion. This anion could be a monatomic anion or could be a polyatomic anion. But if there is a metal cation, you know it's an ionic compound. An ionic compound in aqueous solution will dissociate if it is soluble in water. And remember the always soluble list: all nitrates, all acetates, chlorates and perchlorates, and alkali metal, that is group 1, cation containing compounds are always soluble. Anything else beyond these, you can assume insolubility. One thing to remember here, guys, is like NaCl, according to solubility rule, is soluble, right? So if it is aqueous solution of NaCl, I don't think green shows very well, I shouldn't be using it. If it is aqueous solution of that, then you write it dissociated. But if it is solid NaCl, meaning there's no water in the system, you do not break it and you keep it as NaCl. And that is true for things that precipitate as well. You don't dissociate them. Okay, molecular compounds are ones that are made up of all non-metals. There are no metals in there. Examples are N2O5, PCl3, CO2, all of these. Molecular compounds never dissociate. And water is part of molecular compound, H2O, you don't dissociate it. You keep it like that. For acids, what works is strong acids dissociate and weak acid do not dissociate. Strong acids are list of 7, HCl, HNO3, HClO4, HClO3, HBr, HI, and H2SO4. 1, 2, 3, 4, 5, 6, 7. And everything else is a weak acid. Similarly, so these will dissociate. Similarly, a weak base will not dissociate, but strong bases, which are big B bases. Remember, all group 1 hydroxides and in group 2 calcium, barium, and strontium hydroxides, they will dissociate. Now, let's do a problem to apply all of this learning so far. And with that, we will be done with the reaction prediction part of Unit 7. So, one problem could be a solution of, I'm just making it up on the go, aluminum nitrate is mixed with sulfuric acid solution. So when they say solution, you know it dissolves, right? So aluminum nitrate, AlNO3 thrice AQ, because aluminum is 3 plus and NO3 is -1. Sulfuric acid is H2SO4 AQ, and it's a double replacement reaction. So it'll be Al2SO4 thrice. Remember, the subscripts are determined by charges on the ions, plus HNO3 is the complete molecular equation. I think it's too high. It'll be reduced. Okay, so that is how it will be balanced. Now, if you had to write its net ionic equation, we'll go to solubility rules. Aluminum nitrate is aqueous, so we will dissociate it. So it'll be 2Al3 plus. Now we'll be writing the charge. So this charge is of this, plus 2 times 3. So these two get multiplied. So that will be 6 nitrate plus 3 times 2, 6H plus, that dissociates because it's a strong acid, plus 3 SO4, 2 minus, because this is the charge of this, gives you, now this is a precipitate. They'll have to give you that. You wouldn't know it. So we will not dissociate it. Al2 SO4 thrice plus 6H plus 6 NO3 minus. And now what are the spectator ions? It is nitrate and H plus. So ultimately, what's the net ionic equation? 2Al3 plus 3 SO4 2 minus gives you Al2 SO4 thrice. And that is the net ionic equation. It is an application of the rules that you use. So we use the acid rule to dissociate this. We use the ionic compound rule to dissociate this. So this is all that I have to go over reaction prediction or anything with reactions. Also, if they ask you to make molecular, the particulate level drawings, guys, we've practiced that. You've done those. You have to just kind of translate it into particulate level drawings. Remember, when you mix the two solutions together, the volume changes. So if they are asking of the final molarities, you have to consider the addition of volume. For example, if it is 0.1 molar in 10 mils and 0.1 molar in 10 mils, even though you have 0.1 equal volume. When you mix it, the total volume becomes 20. So to figure out the molarity in final solution, you multiply molarity by volume to get moles, and then see how many moles are forming here using mole ratios, and divide by total volume to get the new molarity. So in particulate level drawings, Nat, you should draw the complete ionic equation because it's important to show the spectator ions on the top unless otherwise specified. So Janani's question, when would it be appropriate to use complete ionic reaction as opposed to net ionic? So if you are doing single replacement reactions, sometimes complete ionic might make more sense. Net ionic makes more sense in case of precipitation reaction, but generally it'll be very rare that you'll write a complete ionic and not a net ionic. You're welcome, Nat. So aluminum, you should know, Shravya. It's 3+, or zinc is 2+. These are the common transition metals. For the other transition metals like Cu or Fe, the charges will be given to you in the compound. So if I write FeNO3 twice, then you know it's iron 2. If I write FeNO3 thrice, you know it's iron 3. So I will give you that information. But for a couple common ones, aluminum and zinc, you should know their charges. Aluminum is 2+, zinc is 3+. Alrighty, guys. From here, I'm going to move on to limiting reactants. And I think limiting reactants is a concept you guys get by and large, and tell me if I'm not right. So I'm going to go over it rather quickly. So limiting reactant is the one that runs out first. And why is limiting reactant important to know? Because the amount of product formed is limited by limiting reactant. So when you're calculating how much product will be formed, you just use the limiting reactants amount. And the second type of question that is asked is how much of excess reactant will remain. And for that, you have to use limiting reactant amount, and using stoichiometry, figure out how many grams or how many moles of excess is used up. And then from original amount of excess reactant, subtract amount used up, and that gives you leftover. It's like you are holding on to, I'm holding on to 3 pens, and somebody uses one of my pens, and how much do I have left over? So I had to first figure out how many pens were used up, and then from my original number, I subtracted the used up, and then I got my leftover. It's the same concept in here. And if you have an excess reactant problem where you are drawing particulate level drawing, you have to be mindful of that to show the excess reactant remaining after the reaction. I think here I'm just going to go over this much unless you have a need for me to go further, because I can do a practice problem if you wish from the practice problems, but I think the concept here is fairly easy. Am I right in thinking that, guys? No one says a thing, huh? Alrighty. Thank you, Ashley. Thank you, Viraj and Animesh. Okay, great. So what I'm going to move on to now is I'm going to move on to Unit 8, do the concepts of Unit 8, which is electrochem. And then I'm going to do the practice problems and then your practice exam if you have done. So let's go to Unit 8. And Unit 8 is electrochemistry. And electrochemistry has 3 different parts. First, we talked about reduction and oxidation potentials and how to calculate E0 standard cell potential, right? Second part, we talked about voltaic cells and how do they function and so on. And the third part was electrolytic cells and electrochemistry, where electroplating and how much things will be deposited, we covered there. Okay, so reduction oxidation potentials, they are given to you in form of a chart, like zinc 2 plus 2 electrons gives you zinc, because Leo goes grr, zinc ions are gaining electrons, you know it's being reduced, and whatever value, I seem to remember, was it 0.34 or was it for copper? Let's make believe, I don't have periodic table in front of me. Let's say it was 0.34 volts, right? That will be its reduction potential. If you flip this reaction around and you write it as zinc gives you zinc 2 plus 2 electrons, then negative 0.34 volts is its oxidation potential. Generally, we use reduction potential only. The only substance that doesn't follow this rule of flipping is water. Its oxidation and reduction potentials are different. They are not the same. Then, other thing, very important thing you must remember, even if you multiply a reaction by 2 or 3 or 4, the value of reduction potential remains the same, because potential is joules per coulombs. As joules increase by multiplying an equation by a multiplier, so do the coulombs. So the ratio remains constant. So for 2Zn 2 plus 4 electrons gives you 2Zn, the reduction potential will still be 0.34 volts if it is 0.34 volts. Okay, so here that was the one thing to remember. Any questions on reduction oxidation potentials? Anything so far on this? Okay, so let's go now to voltaic cells. Voltaic cells are also called galvanic cells, and they are both named after their discoverers. There were 2 scientists that discovered this about the same time, so there's like a contention in scientific community. So some call it voltaic cell, some call it galvanic cell. They're both the names of the same thing. Voltaic cell use a spontaneous redox reaction to convert chemical energy into electrical energy. They are your batteries that you use in all your devices. And here, to make this work, you make the higher reduction potential metal as cathode. So if I say between aluminum and copper, which one should be made cathode? Any one of you have your periodic tables with you, guys? Can you quickly find the reduction potentials of aluminum and copper? Animesh, no, you don't need to memorize reduction oxidation potentials of water. They'll be given to you. Can someone tell me what are the reduction potential of aluminum and copper? 2. Aluminum is negative 1.66. Thank you, Shravya. And copper 2 plus is 0.34. Oh God, then I was wrong here. The zinc was in 0.34, that was copper, okay? All right, so which is the higher value? This one. So we will choose this to be cathode and we will choose this to be anode. Remember, because it's a spontaneous reaction, we do not mix the two halves and we keep them separate. So now, let's say this is our anode chamber and this is our cathode chamber. And in anode chamber, we put aluminum, so oxidation will happen as aluminum 3 plus 3 electrons. And in cathode chamber, Cu2 plus 2 electrons will be reduced to form Cu. So here we will have aluminum strip and we'll stick it in aluminum 3 plus solution. Obviously, there'll be an anion with it. We are just not drawing it. Here we will have copper cathode and it will be dipped in copper 2 plus solution. And in between, they will be connected maybe through a voltmeter. And anode will have a negative sign, cathode will have a positive sign. And you have a salt bridge where the anions like Cl minus will go towards this chamber and sodium ion will go towards this chamber. And as the reaction proceeds, this one will dissolve and become very small. And with time, this one will deposit and become larger. And overall reaction that will happen is you'll have to multiply this by 2 and this by 3 to make your number of electrons equal. So it'll be 2Al plus 3Cu2 plus gives you 2Al 3 plus 3Cu. And if you had to write a shorthand version of it, it'll be Al to Al3 plus salt bridge, Cu 2 plus 2 Cu. That's the net of the reaction. And if you had to calculate cell potential, that will be reduction potential of reduction reaction, which is 0.34 volts, minus reduction potential of oxidation reaction, which is negative 1.66. And I think when you do that, you get 2 volts. And just to double check your answer, if it is a voltaic cell, then E0 cell should be positive. So that is voltaic cell. Any questions on voltaic cell? And the purpose of salt bridge is to maintain charge neutrality. So there's a charge buildup here, and to neutralize that charge, you put a salt bridge in there. Any questions on voltaic cells? Ashley, do we need to know specifics on which electrons move in the salt bridge? So Ashley, no electrons move in the salt bridge, only the ions that are contained in the salt bridge. So salt bridge has a salt. Salt is an ionic compound. So in this case, it's Na plus Cl minus. So Na plus will go here, Cl minus will go there. That's all you need to know, Ashley. Karina, is reduction always on the right side? No, Karina, reduction is not always on the right side. Your cathode reaction could be on the left side. We could decide to draw it opposite. And sometimes they will do that just to play mind games with you. Iris, how will the anode and cathode change in mass? So anode decreases in mass as the reaction progresses because the metal is dissolving to form ions. And cathode increases in mass with time because the ions from the solution are coming on to plate on the electrodes. Any other questions? You're welcome, Iris. So, Bhavik, that's a great question. Yes, molarity impacts the movement and the cell potential. That's called a concentration cell, where in two different cells, you will have the same solution but of different concentration. And one of them acts as an anode, one of them acts as a cathode, but that is beyond the scope of our class and of AP chemistry. So I'm not going to go over it. But if you're curious, then in class tomorrow or at brunch and lunch, I can go over it. You're welcome, Bhavik. Okay, so now the last type, which are electrolytic cells and electrochemistry. So electrolytic cell use electricity or convert electrical energy, electricity, to make a non-spontaneous redox reaction happen. So, you know, a non-spontaneous redox reaction will not happen in its own, but we force this reaction to happen because it's of commercial importance to us. So, if we have single chamber, we don't need to have cells because it's a non-spontaneous reaction. Sometimes, many times in electrolysis, gases form. So electrodes we use are either platinum or graphite. Both of these materials are highly unreactive. They don't react, but they provide an inert surface. And then depending what you are electrolyzing, things will go on anode or will go on cathode. The difference here is, guys, the anode has a positive charge because it attached to the positive terminal of the battery. Cathode has a negative charge because it's attached to the negative terminal of the body of the battery. And on the positive, still oxidation will happen, and on the negative side, reduction, red cat. Okay, so oxidation reaction, you'll be losing electrons. Here, you'll be gaining electrons. So if you are electrolyzing liquid NaCl, not aqueous, guys, there's a difference because in aqueous, there's water too. Then there is selective electrolysis, right? So if two chlorides are losing electrons, they'll form chlorine gas plus 2 electrons, and sodium will accept 2 electrons to form 2 sodium atoms. Okay, so overall will be Na plus 2 Na plus 2 Cl minus gives you 2 Na plus Cl2. If it was aqueous NaCl, then what's going to happen at anode? Water will compete with it, and at cathode, water will compete with sodium. So who wins is water at the cathode because water's reduction potential is higher than sodium chloride. You did this in class on Thursday. And here, what happens is, ideally, you should have seen water getting oxidized, but you actually noticed chlorine forming because it had that smell. And that was because we were conducting this experiment under non-standard conditions. And we had the pencil leads as graphite anodes, right? And when you stuck it in the petri dish in aqueous NaCl, you were actually creating this electrolytic cell and conducting this reaction. Ashley's question, if you're writing the shorthand version, does reduction have to be on the right? Yes, Ashley, that is a convention that is accepted. So in voltaic cell, I'm going back to voltaic cell now to answer Ashley's question. Yes, in voltaic cell, shorthand by convention, the anode reaction is written first, followed by cathode reaction, and it is oxidation followed by reduction. Okay, so Oftentimes in electrochemistry, what is important for us is to figure out by passing how much current, how much substance will be played. So the equation we use is Q is equal to IT. Remember, this T has to be in seconds, and they will not give it to you in seconds. This will be generally in amperes, and the unit of charge is coulomb. So Q is equal to IT. And then the other one is 1 Faraday is 96500 coulombs of charge. And when 96500 coulombs of charge passes, 1 mole of electrons pass through the system. And using these two relationships, you can figure out how much of some substance you will deposit. And last thing, an application of electrolysis is electroplating. If you are electroplating, then the cathode needs to be made up of whatever you are plating, like your spoon if you're electroplating. And the anode needs to be of silver or gold, whatever you want the plating of, because anode dissolves and cathode deposits. And that pretty much is a summary of Unit 7 and Unit 8. And I will be happy now to go over any questions that you have, either in the practice problems. Let's first do the practice problems before we go to the Big Idea 3 test. I would wait and pause before I go over Big Idea 3 test, because those of you who have not taken the test yet, I don't want it being minimized. So let's do practice problems right now, either on Unit 7 or Unit 8. Wherever you have a question on a practice problem, I can do them with you. Oh, I did not, Animesh. Good reminder. I didn't do redox reactions, and I will be happy to do redox reactions. And redox reactions basically are where oxidation number of elements change from reactants to products, indicating electron transfer. And for redox reaction, let's say Cr 3 plus, no, Cr 207 plus Mn 2 plus gives you Cr 3 plus plus MnO2. And then you use series of steps, like first you balance all elements except for hydrogen and oxygen. Then you balance oxygen by adding water. Then you balance hydrogen by adding H+. Then you balance electrons charge by adding electrons. And then you make the number of electrons given by the oxidation half same as the one taken in by reduction half. And that helps you balance the reaction. Okay, number 9 and 11, Shonali, are you talking about Unit 8 practice problems or Unit 7 practice problems? Can you please specify? Oh, goodness, this is a nightmare. So I have a different ID for my channel, so I cannot access any of these things. So let me, do you guys still see me if I open another browser? Can someone confirm that you still see me? So right now my other browser is open. Yes, thank you very much. So let me just log into my drive to access my documents. Okay, so 9 and 11 and 7b. for electrolysis reaction for copper to have I2 bubbles? I will answer. Iris, I'll answer your question too. Shonali, is it Unit 8 practice problems? Can you please tell me? I don't know which one Shonali wants me to do, so I'm going to wait for her to say something. Shravya, is 7B from Unit 8? Is that what we're talking about? I am assuming it is from here, 7B. Calculate the final concentration of copper ion if the cell was allowed to produce an average current of 1 for 3 minutes 30 seconds. So I know in this one, Shravya, for 7B on Unit 8, you cannot calculate molarity because you're not given the volume. But you can calculate the moles. And I have to make an edit, and I edited it for next year. But do you know how to do it, Shravya, if it is moles? Or I can do it with you. So if 7B said, how many moles of copper ion will remain when it was allowed to produce 1 amp for 3 minutes 30 seconds, right? So you know Q is IT and I is 1 amp and T in seconds is 3 times 60 plus 30, right? When you do that, you get a certain coulombs, right? And using these coulombs, then you will say 96500 is 1 Faraday, and 1 Faraday is 1 mole electron, and you need 2 mole electron for 1 mole Cu, and 1 mole, let's just leave it at mole, right? And then you can calculate moles of Cu, and they will need to give you more information, because if they say it is 1 molarity without volume, you won't be able to do it. So what I did is I took this problem from my AP exam and I got rid of the part because there were 2 different concentrations with Nernst equation, and that has been phased out. So I don't think you can do it unless I give you the volume, even for moles, because you'll need to change 1 molarity to moles. But let's say if I said there was 1 liter of it, right? So you know that you started with 1 mole of Cu2 plus ions. And then using this, you'll subtract whatever number of moles of ions you got from here, and that will be your leftover Cu plus moles, or 2 plus. All right, Shravya. Okay. I know how to find the moles reduced. How do we find the final? So final, you start from initial minus, again, how many will be used up, and then that will be that. So number 1 from exercise 11.3 from Unit 8 packet. Unit 8, number 1. So number 1 is fill in the table. Right, Bhavik? Number 1. I wouldn't have, Bhavik, is it possible for you to type the question? I don't have the packet in front of me where I messed up this time. So you'll need to type the question for me and I can do it then. I can answer Iris's question in the meantime. So for electrolysis lab, copper 2 bromide by 2 bubbles form for anode and a black substance form for cathode. Okay, why not the other way around? So copper 2 bromide CuBr2, when you do its electrolysis, there is Cu2 plus and water competing with it, and there is Br2 or Br minus changing to Br2 and water competing for it. And in this case, both of these win. Copper gets reduced and bromide gets oxidized. So what ideally you should see is copper plated on electrode. You will see like on your pencil lead, a little copper looking layer. You will see that clearly. And on the anode, what you will see is witness liquid bromine. So I think what you're talking about, the black thing, that is deep brown bromine that's forming. Bromine is a liquid at room temperature that is very deep brown. So I think probably that's what you witnessed, Iris. Potassium permanganate solutions added to concentrated hydrochloric acid. We need to predict reactants. Okay, Bhavik. So for these kind of questions, that exercise 11.3, you can cross it out because prediction on redox reaction I haven't seen in a while and I don't anticipate that being there. But if I write it like that, hydrochloric acid. So it'll need to be something else. You wouldn't know it. So MnO4 minus to Mn2 plus, and then I'll have to give you something else on both sides. You just need to know how to do this. So that kind of prediction, please cross that exercise out. You don't need to worry about that. That has been phased out. That is not part of the curriculum anymore, Bhavik. So I don't know which 9 and 11 Shanali wanted. I'll probably do 9 and 11 from Unit 8 again. I seem to remember you mentioning in class that we should also be discussing the lab during the live stream. I was just wondering if you're still planning on doing that. I'd be happy to do it. Do you guys want me to do that? Okay, so there were 2 labs we did. The first lab was electrolysis of aqueous solutions. I don't know the exact title of the lab, but that's what we did on Thursday. And in this lab, what you had is you had a petri dish that was divided in 3 parts, and you had 3 different solutions in them. In one, you had aqueous NaCl. In one, you had aqueous Ki. And in the third one, you had aqueous CuBr2. And what you did is you used graphite electrodes and you attach it to a 9-volt battery, right, through those clips, and you put them in different ones and you observe electrolysis in all these 3 solutions. So in case of NaCl, you had on cathode Na plus ion wanting to be reduced to sodium metal, and then on anode you had chloride wanting to be oxidized to form chlorine gas and 2 electrons. But what you have at each of these electrodes is water competing. And water's oxidation potential was negative 1.23 volts, right? And water's reduction potential was negative 0.83 volts. That I remember, but I do not remember sodium's reduction potential. But what I remember is water's reduction potential was higher. So what actually gets to get reduced is water. So what you see on cathode is actually hydrogen gas is being formed, and then hydroxide ions are formed, and the hydroxide ions make it pink around that electrode. So if you did it right, if this is the anode, this is positive, right? And this is cathode, you saw pink color here because of the OH minus that was formed. You also observed some bubbles on the electrode, which were hydrogen gas, because water reduced. Sodium metal didn't form because its reduction potential was lower than water's. Now, what should have happened at cathode is, what should have happened at anode is water should have gotten oxidized, because water's oxidation potential is actually higher than chlorine. But this didn't happen. Instead, what you noticed was chlorine got, there were bubbles of chlorine. And how did you know it was chlorine? Because it smelled like chlorine. You know that smell. And it was enough to make you smell that. So why did chlorine get oxidized even though its oxidation potential is lower or its reduction potential is higher? It got oxidized because we were doing this reaction under non-standard conditions, and their oxidation potentials are not too different. And because of these non-standard conditions, we did not have a 1 molar solution, we had a 0.1 molar solution. And we didn't have 25 degrees Celsius, but we had much warmer temperature in the classroom. So because of those non-standard conditions and because of little difference between the oxidation potential, the chloride ion got oxidized, and that is a common observance. Now let's look at, so far so good for aqueous NaCl electrolysis, guys. Any question? Let me take your questions one by one. Any questions on the electrolysis of aqueous NaCl? While you type your question, I'll write the overall reaction. So will somebody help me out with water's reduction reaction? It is H2 plus OH minus plus how many electrons? So 2, I think, is it? Plus 2 electrons, correct? I think that is what it is. And then here it will be, so this one is being reduced, right? So we have to flip it around. So we'll write it as H2 plus 2OH minus plus 2 electrons gives you 2H2O. And what will be the reaction on the anode? 2Cl minus gives you Cl2 plus 2 electrons. And when we do that, our electrons cancel out, and our overall reaction is H2 plus 2OH minus plus 2Cl minus gives us 2H2O plus Cl2 gas. All right, so that is the electrolysis of aqueous NaCl. That's fine, Animesh. Okay, now let's look at aqueous Ki. So in aqueous Ki, there is K plus and there is I minus, right? So on cathode, K plus wants to be reduced to form K, and water needs to be reduced or wants to be reduced to form hydrogen. On anode, 2I minus want to be oxidized to form I2 plus 2 electrons, and water wants to be oxidized to form oxygen gas. What actually gets reduced is water, and what gets oxidized, I think here is iodine, because when you added starch, there is a property of iodine. With starch, iodine forms a blue color. So what you should have noticed in Ki, when you put your two electrodes. Let's say this is anode, this is cathode. So on cathode, you will see bubbles of hydrogen gas, and on anode, you will see black things here because you have starch in the solution, which with iodine makes this blue speckles looking things. That is a confirmatory test for iodine being formed. An overall reaction here would be again H2 plus 2OH minus plus 2 electrons gives 2 H2O, and 2I minus gives you I2 plus 2 electrons, and 2 electrons cancel out. So it will be H2 plus 2OH minus plus 2I minus gives you 2 H2O plus I2. And the third you can write on your own, but I'll tell you what you were supposed to see. So on cathode, copper 2 plus gets reduced to form copper, and on anode, bromide gets oxidized to form bromine liquid, which is brown in color, and 2 electrons. So the overall reaction is Cu2 plus 2Br minus gives you CuBr2. Here, water has got lower oxidation and lower reduction potential. So water neither oxidizes nor reduces. So this was a carefully designed lab where you saw three different scenarios. One where both ions get oxidized and reduced in CuBr2. One where one ion gets reduced, one ion gets oxidized and water gets reduced. And here it was supposed to be other way around, but they gave you a solution that produces non-standard results. So that was your first lab that you did on Thursday. Any questions on this lab? So iodine and iodide animation are two different things. Iodide is the ion. Iodine is the atom, but according to Hofbrinkel, this doesn't exist and this exists. So when iodide ion gives off the electron, two of them have to give off 2 electrons to form iodine molecule. This is iodine molecule. This is iodide ion. Other questions? Anybody else? Any other questions? All right. Okay, next lab, lab 2 is lab 2 on Friday was electroplating lab. And in this lab, what we did is we took copper 2 plus solution and we put a strip of copper in it and we attach it to a battery. So this is negative, so negative, positive. No, positive is anode. And negative is, then through a wire, I put a key in there, okay? So this is negative. So that was anode and that was cathode. And what we did here is we took different data. We started with mass of key. We started with mass of Cu strip, mass of key, mass of Cu strip. And now what we did is we passed 1 ampere of current for, I forget, I think around 5 minutes or so. And then we took both out, dried them, and now we took mass of plated key. You saw that copper got plated on the key, and we took mass of copper strip. And you saw that mass of copper strip decreased because anode dissolves with time. And where did this mass go? If law of conservation of mass holds true, then this mass went and deposited on copper strip. This mass went and deposited on the key. The mass lost by copper should be the same as mass gained by the key, if law of conservation of mass is true. And I think the results in this lab come pretty close to, very close. You'll see pretty good results. So that was the overall principle here. So using Q is equal to IT, I got how much charge I passed with 1 amperes in 5 minutes. Once I get charge in Coulomb, I use Faraday's to get mole of electron. And then from here, I get mass of copper that should be deposited. So this is your theoretical yield. And then you can say how much was practical yield by finding the difference between the two. And that is what this lab was about, electroplating lab. No, reaction won't stop, Bhavik. He keeps getting coated more and more. What can happen after a while? The mass of deposited copper becomes so heavy that it starts falling down, but the reaction will not stop. It will go on till copper electrode almost goes. Yes. All right, elements. So that is both the labs, some practice problems, concept review. It might be better that I save the questions on the lab and address them with the study session tomorrow. Save the question on the test, Big Idea 3 test, and address them during study session tomorrow, because I have a feeling that many of you might not have done the test yet, practice test on Big Idea 3. Am I right? Do you think it's a good idea to do it tomorrow before or after the study session, guys? Because I think many of you may not have taken the Big Idea 3 practice test yet. Is that correct? I will wait till tomorrow, yeah. Already, elements. If you have any more questions, I will wait a couple more minutes. Otherwise, I'll end this session and I'll see you tomorrow. Don't forget, there is a study session, 3:30 to 5:30. I got a bunch of preparation for the study session tomorrow. I'm ready. Yeah. Are you? Okay, so bring your cushion, bring your comforters, bring a throw blanket to sit on the ground, because I think the space will be limited. You are welcome. I know you guys like the junk. One day junk won't hurt you. Alrighty, guys. Are there any other questions? You're welcome, everybody. I think you guys are good. Okay, I'm going to end the stream here. And then remember, we still have tomorrow. I'll just give you 2 lab questions to do in class. But even with that, we should have some time for question answers. Already, elements, good night. I'll see you tomorrow.